Okay, so today we're going to look at three of the routing protocols that we discussed earlier, the dynamic routing protocols. So we're going to look at the three: RIP, OSPF, and EIGRP. We're going to understand the basic concept about each. The basic concept of each dynamic routing protocol and how to configure it. And basically, we're going to start with RIP, which is Routing Information Protocol. So, as I have said earlier, this just it's just it's just a dynamic routing protocol, and it uses op count as the routing metric to find the best path between the source and destination. So basically, RIP uses op count. So that what that means is that whenever there are three routers, let's say I have 5 routers and they're connected like this, and let's say this is router 1 and this is router 2. So for RIP, it will use the best path to reach router 2. For example, op count. So op count basically means it will use a path with less routers. So for example, this one is sorry, I'm going to do something here to explain it better. Okay. So let's say there was another router here and it's connected this way and to router 2. So let's assume router 1 wants to send a message to router 2. So we're using this routing protocol RIP. How will router 1 find the best path to router 2, being that there are two paths, going this way and going this way? So RIP uses hop counts, a path with less hops, with few hops to the destination. So for example, the first path has 2 routers, then to the destination. But the second path has only one hop to the destination. So RIP will use this one, a path with few hop count to the destination. So I will see that it's a distance vector routing protocol. Distance vector routing protocol means that it uses a path with less hops. So the distance, whenever there's less routers in the path, RIP assumes that the distance is less. So it uses that as the metric. So it has the administrative distance of 120. So it's very, very important to understand that RIP is a dynamic routing protocol and it uses hop count as the routing metric. And another thing that you have to understand is that RIP is a distance vector routing protocol and it has administrative distance of 120. So these are not important, but you have to know them, the port that RIP uses, and it works at the application layer of OSI model. This is wrong. RIP works at the network layer. RIP is a routing protocol. So let me just pass that for a minute. So there are 3 versions of RIP. We have RIP version 1, version 2, and RIP next generation. So we have features of RIP. For example, updates the network exchange periodically. That's okay. Updates are always broadcast. So that means that whenever this router receives any update, it will send to all the routers in the network broadcast, and it is periodical. And full update tables are sent in updates. So for example, this router received that update, it sent all the routing table to this router and to this router. Routers always trust on routing information received from the neighbor. This is also called routing on rumors. So for example, when router 1 has received updates and is going to advertise or rather send the updates to the neighbor will believe that whatever they receive from router 1 is correct and there's no error in it. So that's what we mean by routing on rumors. So basically, let's understand the next routing protocol, which is Enhanced Interior Gateway Routing Protocol, which is EIGRP, which is very, very important, you know. The first thing that we have to understand is advanced distance vector routing protocol. Remember, RIP was just a distance vector protocol, but this is now advanced distance vector protocol, and it supports routing and VLSM. VLSM is variable length subnet mask, kind of subnetting that we were doing, and also it supports route summarization, incremental updates, load balancing, and many other useful features. The most important part of RIP is that it's Cisco proprietary protocol. It was developed by Cisco. So all routers in the network that is running EIGRP should be Cisco routers. So it was basically introduced or developed by Cisco Group for their networking facilities. So routers running RIP must become neighbors before exchanging routing information. So for example, in this diagram, if all of these routers are running RIP, then they must become neighbors. They have to become peers. They have to become friends so that they know the status of each other in order to communicate, because they cannot communicate to a stranger. They have to know like status of each other. That's what we mean by they have to become neighbors in order to communicate, and they use a multicast address of this one. So RIP as EIGRP has administrative distance of this one 90, and it uses this protocol to send messages. So you see in RIP we had administrative distance of 120, but in EIGRP we have administrative distance of 90. So we see that also EIGRP calculates its metric by using bandwidth, delay, reliability, and load. And by default, only bandwidth and delay are used in calculating metric. You know, these are mostly asked question in CCNA exam. The metric, how to RIP calculate its metric. We saw that it uses op counts, a path with few ops to the destination. But in EIGRP, we use bandwidth and delay to calculate the metric. And also, EIGRP uses the concept of autonomous system. Each router inside autonomous system must have the same autonomous system number configured. Otherwise, they will not become neighbors. So autonomous system is just like an area of application. Your ID, for example, in USA, you have a telephone. Your mobile number set from +1. So if I come to USA with a Kenyan number, I cannot be able to communicate there because USA format is +1. In Kenya, it's +2, +254. So autonomous system number is just something like that. Phones in the same country must have the same format at the beginning, 2+1 or +254 in Kenya. So that's what we mean by autonomous system, area of application. Okay, then we have to understand
that like for autonomous system. That mean they have like the protocol, the same protocol for all the lines in the country.
Well, autonomous system doesn't mean a protocol. It's just like a number. So whenever we say that we have to group these students to number 8, so let's just speak in terms of classes from class 1 to class 8. So somebody in class 1 cannot understand a student at class 8 because they belong to different autonomous system numbers. They belong to different classes. So autonomous system is just a way of grouping nodes or people or anything together so that they are unique from other groups. So I was trying to use a case study of phone numbers, mobile numbers. In USA, you use something like +1. In Kenya, +254. So I was trying to say that when I come to USA with my mobile number, I'll not be able to communicate because the autonomous system number there is different from my autonomous system number. So just a kind of grouping. It's not a kind of protocol. You can put any number. So for example, let's say autonomous system number 10, number 11. You can just put any number. It's not restricted. So it's not something to deal with protocol. It's just a way of grouping things. You have to group them number 10. You have to group them number 20. Like that. You understand that?
Yeah.
Okay, so EIGRP, we have tables. In a routers, we have table, we have a neighbor table. We saw that when these routers want to exchange information, they have to become friends. So the friends are stored in neighbor table. Topology table. Topology stores routing information run from the neighbor routers. So for example, you add some information, I store it here. Although I will store your name here, but all your information, for example, when you have a laptop, a bag, your clothes, I'll store them in topology table. And the routing table, I'll use to store the best path to reach you or to reach the destination. So you have to understand these different tables. Very, very simple. Okay. So I can see ERGP is a lot, but I'll just try to summarize them. So for example, in ERGP we have packets. So we have hello packets, update packets, we have query packets, reply packets, and acknowledgement packets. So hello packets is just used to discover a neighbor. For example, when you say hello to someone and they reply back hello to discover the neighbor. So update is used to send a routing updates. For example, when I have received any updates and I want to let you know, I use this update packet to send you the update that I have just received. Query packet, it's used for asking any routing update. For example, you want to ask me, did you receive any update from the teacher? Well, if you use query packet to ask me that. Reply packet, well, I'll use the reply packet to reply your question. And finally, acknowledgement packet. Whenever I reply your question, you have to acknowledge it. Thank you for replying me. And that's all about the packets. And I'll send this note so that you understand them better. Yeah. So there are states. So for example, these are very advanced. We saw that it's advanced distant vector protocol. So it has a lot of notes to discuss, but I'll just try to summarize them so that we can go to the configuration part. So we have passive and active state. So destination the topology table can be marked as the way that I've just said. So in passive state, when the router has identified the successors for the destination changes to active state when the current successor no longer satisfy the feasibility condition and there's no feasible successor identified destination. Well, I think this part you have to understand it here. Feasible. I passed this part. Unfortunately, I passed this one before we could understand this one, because it's better to understand this one first, then we come to this to understand what we mean by feasible successor and the successor. So just a minute, sorry for that. We have what we call feasible and reported distance. So feasible distance is the metric of the best route to reach a network, the route listed in the routing table. So for example, feasible network. So for example, this is router 1, router 3, and router 2. So this is the feasible distance. And this is advertised or reported distance. It's just simple as this one. Feasible distance to router 3, then advertised distance to router 2. Just that way. Then what we have what we call successor and feasible successor. Successor is a route with the best metric to reach the destination. And that is stored in the routing table. Then we see that feasible successor is a backup path to reach the same destination that can be used immediately if the successor fails. So we see that successor is like a main path, but when the main path dies, we carry on with the feasible successor. So for example, here to here. Initially, let's assume this router is using this path to forward traffic to this PC. So this is the successor. But whenever this path dies, we have feasible successor, which is the backup. So it's just very simple like that. Feasible successor, successor is the main path, the primary path. But when the primary path dies, the feasible successor, which is the backup path, picks up. Now we can now understand this one. So we see that in passive state, inactive state means that we have successor. The primary path is working. But when the primary path dies, passive state gets in, which is feasible successor, the backup path. Okay. Then we have the ERG configuration. I'll delete this. I will delete this because this is just shallow, and I'll leave you with this when I will be sending this document. But all of this we're going to look at them during the configuration part, so we don't have to worry about them. I will explain later. So for example, in this topology here, and just a quick explanation. In this topology here, we want to configure EIGRP. The first thing that we do, we make the router aware that we are using ERGIP as the routing protocol, and we group it with autonomous system number. So that's where autonomous system number comes. You can put any number so long as the routers in the topology have the same autonomous system number. They're in the same country and they can call each other because they have the same phone format, mobile number format, or they are in the same class. Let's say primary class 2, and they are taught the same subjects, so they can communicate, understand each other, something like that. Just group them together because they are in the same, how can I say, in the same domain. And also now you advertise the networks. You make the router aware that I'm advertising this network and I'm advertising this network. So it's very, very simple. Only these 3 commands and we're done configuring EIGRP. What you have to understand, make the router aware that it's using EIGRP as the routing protocol and specify the autonomous system number. After doing that, advertise any network that is directly connected to the router. in this router there are only two networks, this one and this one, and they are advertised here. All right. And finally, let's look at this interesting routing protocol, which we call OSPF, Open Shortest Path First. We see that this is a link state routing protocol, and it is open standard. In the previous protocols, they were distance vector routing protocol, but this is a link state routing protocol. And we saw that EIGRP is Cisco proprietary, but OSPF is open standard. And we see that just like EIGRP, routers running OSPF have to become friends. They have to establish neighborship first before they can exchange updates or routes. Another point, sorry. We see that OSPF is a link state routing protocol. So it doesn't exchange routing tables, but instead it only exchanges the about network topology. You know, a routing table is like it's very huge, so it doesn't change. It contains everything. Let's say in that router, a routing table contains everything, every entry. So it doesn't exchange that everything. It's only exchange the change that happened. For example, the topology change that happened during that time, but not everything. It doesn't exchange everything. It only exchange a specific topology change that happened. For example, there's another network that has been added. It's only exchange that network that has been added, but not everything that was there previously, because we assume that during the neighborship relationship they had exchanged everything, but now when they are now running, they should not exchange everything now, because it's like a repetition. They should only exchange what is new. So that's what we mean there. So we see that each OSPF router runs this protocol SPF, which is called shortest path first algorithm, to calculate best paths and to add the routing table. So it's this algorithm SPF that is used to calculate the best path to reach the destination. Then we see that because each router knows the entire topology of the network, the chance of routing loop occur is very minimal. So this is why in my topology or in my recommendation, I always use OSPF, because it's open standard, it's a link state routing protocol, and it has a faster convergence, and loops doesn't occur. The chances of loop occur very minimal. Then features, we see that it's a classless routing protocol. We can do subnetting and apply to the networks, and also it supports this one. So this just the two just relates to this about subnetting, then route summarization, then equal cost load balancing. So for example, equal cost load balancing basically means that whenever there are two paths to the same destination, and sorry, sorry, I'm suffering from some cold here. You know, I got cold the previous day. Yeah. So equal cost basically means that whenever there is two paths to the destination, and one path dies, another one will pick up, or whenever there's too much data passing through one path, so it can load balance so that some data pass through the other path. That would mean that equal cost load balancing. Then incremental updates are supported. That's okay. Then it uses one parameter as the metric. So we see that in RIP, it was using op count as the metric. In EIGRP, it was using bandwidth and delay as the metric. And in OSPF, it uses the cost, the interface cost, as the metric. So what's the metric? Metric is just a way of defining the best path to the destination. How does it define the best path to the destination? It uses the cost. A path to the lower cost in OSPF, a path to the lower cost is used as the best path. In RIP, a path with the less ops to the destination is used as the best path. In EIGRP, a path with the lowest bandwidth a path with the highest bandwidth and the lowest delay is used as the best path. So OSPF has the administrative distance of 110, RIP add 120, EIGRP add 90. And he had some multicast addresses here. OSPF also had a lot of nodes here. So in OSPF also we had three tables just like in EIGRP. We said that neighbor table we use just to keep your name. In topology table we used to keep what you have. You have bag, you have your books, you have your laptops. You keep it there. Then shows this topology structure of the network. And the routing table, we use the best path to reach to you, to reach to your house. Things like that. All right. So what do we call OSPF neighbors? Well, OSPF neighbors, routers running OSPF protocol needs to become neighbors so that they can exchange information, because you can't exchange information to anyone you don't know, strangers. So they use hello packets to send to discover neighbors. So hello packet is very, very important. It's used to discover neighbors. So these are various packets in OSPF. OSPF has hello packet, the one that is used to discover and maintain neighbor relationship. Then we have what we call database description packet, which is used to describe the topological database content. Then we have link state request packet, which is used to request the piece of information from the neighbor database. Then we have what is called link state update packets, which is contain the list of link state advertisement to be updated. Then we have a link state acknowledgement that is used to acknowledge the receipt of packets. So for example, between this router and this router, each of them will send hello. Each of them.
Hello?
Yes.
Oh, did I?
Yes. I'm saying
okay.
they have hello packets. Yes. Each of them will send hello packets. So after each of them have sent hello packets and they have greeted each other and maybe they have become neighbors, so they will start advertising their content. My name is so and so. I come from this place. That is used. That's when they exchange this packet. Database description packet. Hello is just for establishing a relationship. So giving more information, we use database description packet. So after each of them has given any information it has, so router 1 will check that I need to request router 2 for this kind of information. Maybe router 2 has given an information that is very, very important for router 1. The router 1 will request that information. That's when it uses link state request packet. I heard that you come from let's say Texas, Dallas, Texas. Can you just give me this kind of item? Yes, I can give it to you. So Whenever that router 2 is giving that item that has been requested by router 1, it uses this packet, link state update request, and router 1 will thank router 2. Thank you for giving you the item. It uses link state acknowledgement packets. So that's just kind of a demo. Then we have neighbors states. OSPF is a very broad protocol, and I will need you to understand it better, because this is where most of the exam come from, because OSPF is the most widely used routing protocol. It's open standard, you can use it anywhere, and it's very broad. So we have several neighbor states. So for this neighbor state, they're self-explanatory. I'll just leave you to understand them so that we proceed to other things. The most important thing here also is OSPF areas. I don't want to pass this area, this place, because it's very important. Just like I said that in EIGRP we have what is called autonomous system numbers. We group things according to, how can I say this? We can group people according to their age. We can group people according to their language. We can group people according to their wealth status, things like that. Autonomous system number. So in OSPF, we don't call them autonomous system number. We call them area. So let's say, just in terms of age. Let's say in terms of age, this group area 10 represent people with the 10 years and above. Area 0 represent people with below 10 years. Area 20 represent people with 20 years and above. So that's what we mean by area. In EIGRP, we call them autonomous system number. But in OSPF, we call it area. It's just a kind of grouping according to a specific similarity, maybe. Okay. So OSPF uses the concept of area. So area is just a logical grouping of contiguous network and routers. And all the routers in the same area have the same topology table, but they don't know about the routers in other areas. So, for example, all people under area 10 is 10 years and above. All children under area 0 is between 0 and let's just say below 10 years. All people under area 20 is 20 years and above. So the main benefit of creating areas is that the size of topology and the routing table on the router is reduced, so that we don't mix grouping is a very important thing, and in business I believe you know what grouping means. If you don't group your things are just going to be messed up, and it's very hard to identify and manage them. So it's required less time to run this protocol, this algorithm, and routing updates are reduced. So for example, these people are just going to communicate inside here. These people are just going to communicate inside here. These people are not just going to communicate inside here. They are not going to communicate randomly, just inside the area. Alright. So these are not important so much in our configuration, but you'll have to read about them. Okay. So after I've done that, I'll just proceed to our packet tracer and redo the configuration. Okay. So I have my packet tracer on here.